Have you ever wondered what's really keeping your feet on the ground? Or what keeps the moon locked in its orbit and entire galaxies from just flying apart? Well, it's all down to a single invisible force. And today, we're going to decode the master rulebook for that force, Newton's law of universal gravitation. So let's start with this classic question. On the surface, these two things seem totally different, right? One is this everyday thing, happens in your backyard. The other is this silent cosmic dance happening thousands of miles away. But the genius of Isaac Newton was realizing that the exact same force was behind both of them. Let's dig into how. And this is the core idea, right here. It's pretty straightforward when you think about it. Everything that has mass pulls on everything else that has mass. It's not just a thing for planets and stars. It's a universal law of attraction. Honestly, this one sentence completely revolutionized how we see the entire cosmos. Okay, but how does this attraction actually work? What are the rules of the game? To get that, we need to pop the hood and decode gravity's mathematical rulebook. And here it is. That's the rulebook. Now, I know it might look a little intimidating, but don't worry, it's actually telling a really simple story. You see that F on the left? That's our hero, the force of gravity. Everything else on the right just tells us what makes that force stronger or weaker. Let's break it down piece by piece. So the whole thing really just boils down to two big rules. First up, mass. It's simple. The more stuff you have, the stronger you pull. More massive objects mean a stronger gravitational force. If you double the mass of one object, you double the force. Simple enough. But the second rule, distance, well, that's where things get a lot more dramatic. And this is where gravity's power really shows its cards. The force doesn't just get a little weaker as you move away. It absolutely plummets. This is the famous inverse square law. So if you double your distance from something, the force isn't cut in half. No, it drops all the way down to just 1/4 of what it was. That tiny little squared symbol in the formula is the secret ingredient that explains why gravity's influence fades so quickly across the vastness of space. So what about that big G in the formula? Well, that's the gravitational constant. You can think of it like a cosmic translator that turns our numbers from mass and distance into the actual force we'd feel. And just look at that number, it is unbelievably tiny. This is so important. The reason you don't feel the gravitational pull of your computer or the person next to you is because G is so incredibly small. It basically means you need a planet-sized amount of mass for gravity to become a big deal. All right, now let's see this law in the wild. We're going to compare two totally different scenarios to see how this plays out. We're talking the human scale versus the cosmic scale. This is where the numbers really start to tell the story. Which, of course, brings us to the big question you're probably thinking right now. If this law is universal, why aren't we all just getting pulled towards each other? Why does gravity only seem to pull us down toward the Earth? Well, the answer is all in the numbers. Let's do the math. Let's say we have two students, both about 50 kilograms, sitting just 1 meter apart. When you plug those numbers into the formula, the force you get is, well, it's this. It's an absolutely minuscule number. We are talking about a force that is way weaker than the push from a single mosquito. It's so tiny, it's completely, utterly unnoticeable. But now, let's swap out one of those students for the entire planet Earth. Whoa. The gravitational force from Earth on a 1,000 kilogram satellite is about 8,200 newtons. That is a huge force. It's like lifting a large SUV off the ground. And think about it. The only thing that really changed was the mass. And that, right there, made all the difference. And that massive force we just calculated, it actually has a special name you already know. Weight. That is all weight is. It's not really a property you have. It's a relationship you have with a planet. Your weight is literally just the measurement of Earth's gravitational pull on you at this very moment. Okay, so this is obviously more than just an abstract theory for a physics class. This law is, and I'm not exaggerating, the bedrock of our modern world. Let's take a look at how we actually put gravity to work. I mean, think about it. Without a deep understanding of Newton's law, we could never place a satellite into the perfect orbit for your GPS to work. We wouldn't know how much thrust a rocket needs to actually escape Earth's pull. And even right here on the ground, engineers use it to design buildings that can support their own weight against gravity, and scientists even use tiny variations in gravity to figure out what's going on deep inside our planet. Okay, let's do a quick thought experiment. This will really help lock in that powerful inverse square law.
Imagine Earth suddenly puffed up, inflating to twice its current size, but its total mass magically stayed the same. What would happen to your weight? Go on, take a second to think about it. All right, you got an answer? Let's walk through it. We start with our basic rule. Now, since the new radius is 2r, we just plug that into the formula where r used to be. But here's the crucial part. That whole thing gets squared. So 2r squared becomes 4r squared on the bottom. And there you have it. The new force of gravity would be just 1/4 of the original. You'd feel 4 times lighter just because you're twice as far from the center of the planet. And that's really the beauty of it all, isn't it? From the almost non-existent pull between two people in a room, to the colossal forces that keep entire planets tethered to their stars, it all comes down to this one simple, elegant, and universal rule. It's just a stunning testament to the underlying order of our universe. So I'll leave you with this one last thought. That distance in Newton's equation, well, it has no limit. The force gets weaker and weaker and weaker, but it never ever truly hits zero. And that means that your mass, right now, wherever you are, is exerting a tiny but very real gravitational pull on the moon, on Jupiter, and yes, even on stars in the Andromeda galaxy. So the next time you look up at the night sky, remember, the cosmos is pulling on you, and you are pulling right back.